My name is Santiago. I'm a research scientist at Caltech. I've been there for about 16 years. My focus is doing scientific visualization. What I do is I collaborate with different researchers around Caltech, whether it's geophysicists, biologists, material science people. And I help them either create complete tools, algorithms, exploratory environments, portals, sometimes just illustrations and movies that they can use either to understand their data better or publish their data. And in that process, I've been so bombarded with data, and it's got such cool origins and so much deep science inside of all this data that it's hard not to start kind of deviating and find beautiful moments, artistic moments in here. And I've kind of developed my own art because of that. And so today I'm going to talk a little bit about visualization, the things that I do, and then a little bit about those detours that I have taken into art. So hopefully it's not too all over the place. So let me start by talking a little bit about what visualization is. Visualization is basically just translating information into a more understandable format. Most of the times that means putting somewhere visually. It could also be audio or touch feedback, despite the name visualization. But I think the best example that I can show you what visualization is actually an art piece that was made by Evan Roth. He was flying across the coasts, and he was sitting in his seat, staring at his tray, like we often do, and he started figuring out, is there something interesting to do? And he looked at his Skyball magazine, and by the way, that's not Evan Roth, but that is the magazine he used. And he decided to rip out the faces from the magazine and start kind of figuring out what the demographics of the models inside the magazine were. And he came up with this illustration, this visualization. Here he's showing the faces from small to large. Here he actually divided the faces between men and women, so you can see who the target audience is. Maybe you don't, I don't know. Here is a visualization between dark haired people and light haired people. And the most interesting one that he came up with was this one, which is white people on one side and us the rest on the other side. So it's definitely uneven. But the cool thing is that he's presenting to you the data. This is the data. The faces are the data. He's not manipulating them. He's not changing the color. He's just doing a visual composition of that. So there's definitely an artistic ability here. But he's also telling you a story, at least with the last picture. He's telling you a very clear story that hopefully SkyMall magazine has fixed by now. There's definitely a lot of art. There's understanding of the data. You have to understand where you're coming from. And that's all what visualization really entails. So visualization is really about understanding your data and what you're trying to show your audience. And yes, visualization actually is not new. It's been around for thousands of years. The first visualization was probably 6,000 years ago when they were drawing maps and you showed rivers and fluid flow. So you actually use little glyphs to actually show the way fluid goes, wind patterns. An interesting visualization is this act was actually done about 500 years ago by Galileo. Sorry, 400 years ago. And these are actually sunspots. So he actually looked at the sun for 35 days and he drew the sunspots. And it wasn't an animated GIF back then, but it's pretty amazing, especially when you put it in the flipbook kind of idea, seeing this kind of sunspots happen. So visualization has always been very closely tied, so visual elements are always been close tied to science because science is complex. So putting a visual format on it always helps. So visualization really does have a lot of power to help explain things, especially complex things. About I don't know, 300 years ago, in the 1800s, Florence Nightingale, who's the mother of nursing, she was also a statistician, and she actually drew what's now called the Nightingale Rose, which is basically a pie chart combined with a histogram. And she was actually trying to show the Queen what the composition of the people dying that were coming to her hospital around the Crimean War. So in black, you see the people that died from from other causes. I don't know why I started there. From blue is the people that actually died from transmittable diseases, preventable diseases, and from red are the people who actually died from wounds. So you can clearly see when the Crimean war actually starts on the right side, you actually see kind of a big increase in people who actually die from wounds, and you see kind of also in the bottom you were able to see that there was a lot of communicable diseases that people were dying from in the winter months. So this one picture just tells you so much information that if she was to give the queen a table of data, it would just, it would be really hard to try to tell any particular story. So visualization is really truly powerful. It's been around for a while, and then the question is, okay, so what makes good visualization? What makes effective visualization? Well, we have what's basically the modern parent of scientific visualization. His name is Edward Tufte. He's a statistician at Princeton, and if anybody's keeping checks, if you mention Edward Tufte, then you get a little check for visualization presentation. It has to be there. I couldn't avoid it. Anyway, he's basically curated all the best visualization work out there, and this one is one piece that he actually called the best visualization ever done, the best infographic. And the reason is it's an illustration from 1861 done by Maynard, and actually shows the advance of Napoleon onto Moscow. So here's the elements that it has. This beige bar, the width of it actually is the amount of troops that he had. He's moving eastwardly towards Moscow, and as they advance, they start losing people. Eventually, they do a split, have them go to Poland. They keep on advancing, and they just keep on losing people and losing people. It has lines pointing to the bottom, actually showing the temperatures as they advance. So obviously, you're going into Russia. Once you get to the winter months, pretty much all your French people die. And then you get to Moscow, and you say, let's retreat. And they did. And as they retreated, they kept on dying. And you see the geographical elements with the rivers. So it's basically a motion piece, right? You see, it's dynamic. It shows all this amazing amount of information, and it's very precise. It's very clean, and that's what Edward Tufte is all about. He's saying that visualization really needs to be clean, crisp. Just have the information that it needs, no chart junk, as he calls it. And you can definitely see that why he would call this one of the best infographics ever made. So that's what people strive in the visualization field, to have a smile from Tufte. But the truth is that even this visualization field is just like the slide that we were showing before, is science and art and communication, graphic design. And you can really live anywhere in this space. You can be a visualization person and live in the scientific world. You can be a visualization person and do infographics for the New York Times or the Economist. So it's very about heavy on design and communication. Or you can be all about art, where you start ignoring the origins of the data and just use it as a source to actually create interesting information, interesting art. So for the most part, people kind of debate which is when you talk about it, they debate, where you stand in this space. For the most part, I work at Caltech, so I have to please, my overlords. So I'm very much about staying true to the science and staying true to the data. But every now and then, I do take the deviation into the art world, where I might or might not keep true to the science. And that's what the next three things that I'm going to talk about. Pragmatic visualization, what I call pragmatic visualization, is definitely visualization which is in a timeline. Because we're in a scientific world, we need to publish our results. We can't spend too much time creating, a Maynard-like visualization that's super complex and clean and perfect. Sometimes you just have to publish the results and get them out. So we definitely have to keep on top of it and be as quickly as do things as quickly as possible. This is a sample visualization that I did for one of the projects that we did, and it's a projectile going through a plate. What's amazing about it and really cool about it is that it was one of thousands of simulations being done, and we not only did the simulations done on the largest computer by the national labs, but we actually did them, and we had experiments of the same type of materials going through the same type of plates, and the simulations kind of adjust themselves to get as close to the reality as possible. So at some point, the simulations can tell you, you know what, our simulations are this close to reality. And if we change something, if we make the plate thicker or the bullet go at a different angle, we can tell you how close we are to reality. That to me is just completely mind-boggling, because it means that we're getting to the point where we can tell you that anything you ask us, we can create a simulation, and we can tell you how close we are to reality. Anyway, that was a tangent. But yes, I make the pictures for this. It's massive clouds of points, and they're actually points that are actually not solid meshes, which is just what they thought was appropriate for this kind of thing. And that's the kind of thing that I do on a regular basis. But it's not all 3D plots, and this one was meant to look like X-rays and shadow graphs that they use. Lots of times it looks more like this, like a plot line. And the question is, can you make one of these plot lines sexy? And the answer is yes. So you just have to know where it's coming from. So this particular thing, for instance, is actually a visualization of DNA interacting with itself. So you know about the DNA sequence. These are places where the DNA is touching itself. So this actually means that there's a structure. That was funny, yeah. That means that DNA is actually coiling itself and actually creating a 3D structure in space, and that's where these little peaks, these little red dots are. So we're getting to the point where we're understanding the actual 3D structure of DNA when specific things happen. So all of a sudden, this one ugly plot all of a sudden becomes a lot more interesting. It becomes a lot more exciting. This is another plot that this one is of the earthquake that happened in Sumatra. It was an 8.9 earthquake that created a tsunami that killed about 1,200 people. This is my artwork that made it to the cover of Science magazine. And visually, it's not stunning, but again, you think about the simulation that was done to actually figure out how this earthquake actually traveled the plates and actually traveled the Earth up 2 or 3 times before it completely dissipated. It was a massive earthquake. And we created a visualization and an understanding of simulation of what this stuff works. So even a simple plot, once you give it the meaning, especially in the world of science, it can be pretty strong and pretty powerful. This is, again, going back to the RNA stuff, this is just a matrix of interaction. So the moment you start adding color to it and you start looking at it, you can kind of divorce yourself from the original meaning, and it just looks like a cool color blob. So kind of like when you look at a Rothko, you get inspired, you get different feelings. Here, you can look at one of those things, and eventually you can start thinking of interesting things. So I think that art can be found in science very easily. And that's kind of brings me to one art piece that I did. So I was doing some volume rendering, which is the ability to actually visualize volumes by bombarding them with light and then coming up with light with what it looks inside. This is a fluid kind of interacting with itself, not touching itself. This is another volume rendering of a mouse embryo. But it's this whole process to actually do volume rendering that I looked at one of these simulations that we're doing. I came up with this art piece that has this amazing motion to it and these waves that you don't need to know what it is. It just looks like an interesting landscape that you can stare at for a while. If you actually knew what it was, you also start learning, yes, it's a shockwave going through a metallic wedge, like imagine an atomic shockwave kind of vibrating, a concrete wedge. So it has this all interesting flows and shocklets, and shocklets is a small shock wave. So it has really cool things to it, but as an art piece, I think it stands for itself, and it's quite, I think, cool. So that's one art piece I did. Kind of going from a different point of view, I also create tools. So I was doing some work with some planetary scientists, and they were analyzing what it meant for little particles to fly from Mars and make it to the Earth. And they figured out that if there was an impact strong enough on Mars, it could actually impact and the pieces could go flying off. So the visualization itself is kind of plain, the colors are plain, but the science that went into it is so strong and cool, it made the cover of of Nature magazine. But this whole idea of drawing points, even the planet is actually modeled as point, not as an actual mesh. So this idea of drawing points kind of took me to this space of, okay, maybe I can create a better tool to render points, and thinking of this duality between points. if you have enough points, it can actually become a solid object, at least in this world of scientific simulation. And I created this art piece where it's a continuous rendering of superfast too, of spheres. And once you put enough of them together, it starts looking like a string, like a tube. And it actually crosses boundaries. Every time you can follow it, it goes from one side, it bounces, and it goes on the other side. And it has depth to it, it has movement to it, and it has this whole duality of particles becoming objects. It's a series of pieces. And it's pretty cool to have, a 5-year-old try to trace the line. So that's another art piece. And the last art piece that I'm going to talk about is some work that I'm doing with some biologists. So they're actually trying to study when generic embryonic cells all of a sudden become specialized, become particular types of cells. So they have these plots where they look at just one piece of the DNA and they see how they interact with each other. They throw these arcs. Once actually something starts happening, the arcs start jumping all over the place. It looks this ugly. So I went in and I said, okay, first of all, let's clean it up. Let's create an interactive tool that's a little more, gives you a little more information. And I created this, but having this ability to show one segment just didn't seem enough. We have a massive amount of data. So what would it mean to actually visualize the whole genome? So I went ahead and tackled that problem. And this is actually the whole genome being visualized. So if you actually printed this out, it would be 1 foot tall and 1 mile wide. And the amazing thing is that we use this format called SVG, which is like Illustrator kind of thing. And a browser can actually handle this size file. So you can actually open these files in a browser and search them and look through them. So if we start zooming into one of those little sections, you can see you can open it up and open it up and open it up, and you get this picture of these interactions. And you can scroll it, search through it. There's all these other cool things, but this wasn't enough because I wanted to be able to have it in my hand. So what I decided to do was to go ahead and coil each of the chromosomes. A mouse embryo has 18 chromosomes, and we coiled each of these chromosomes into spirals. So there's a bit of theme of spirals in my work. I don't know why. And what we have is actually 3 stages of this mouse embryo changing, and it's created into a continuous spiral, spiral that continues to the next spiral, continues to the next spiral. So rather than having a mile-wide thing, we actually printed this on an art piece, and it was showing in the Williamson Gallery at Upper Art Center until last week. And it actually, you have the ability of walking next to it, and your perception, just as you walk through it, you start picking up arcs that are in the top picture but are not in the bottom picture. And not only that, but I actually printed on vellum, so if you took it out, you could actually put it on top of each other, like a map, and you could actually see the differences. So there's definitely space to actually create solid things, art pieces that still kind of have a little bit of science in them. And I think the idea of showing this much scale in one art piece was also pretty cool. And this is what it looked like actually showed up in the gallery. Okay, so science, you look at it, you come up with pretty pictures. You can call it art. So where is this going? What else could you do? So just as an idea, about 16 years ago when I joined Caltech, we had this thing called the responsive workbench, which is basically a projector that would, through this mirror, it would show an image on the screen, and you would put 3D glasses, and you actually see objects as if they were floating on top of the table. And it was one of the most realistic virtual reality experiences that I've ever had. But the problem is that he had very small space where the object would exist. But it was very cool. It was so cool, in fact, that we have an artist here, Jim Barry, that actually worked with an environment to actually create art in this space. And it was very effective, it was very cool. But as the technology just kind of passed on and the machines got old, we kind of killed this machine. But what's next? Well, just last week, Microsoft announced the HoloLenses, which is kind of like the Oculus Rift or the Google Glass, but they've actually been working at this for about 5 years. I think their budget was about $1 billion. And JPL actually had these things for about a couple of years. They weren't allowed to talk about it. And I've heard that it's what you expect to come out of virtual reality. It has the API, it has everything, so you can actually create experiences within this space, and you can make it basically today. And so it becomes a very exciting technology that you can think of what it means to either have art projected, being immerse yourself in art, or even create spaces where you can create your own art. JPL actually has a demo of Mars rover and walking around the rover and kicking the tires or something. But they definitely feel that this is the crossing point, the threshold where virtual reality, not for the whole world, but for very specific applications, can be very successful and very powerful. So the same perception ideas that we get when you look at an art piece now can be expanded into this virtual reality world. These massive amounts of data that we're collecting, we can process them and bring them into this thing. So it just creates this fertile ground to create some really cool things. And I think there's a big space to actually do some cool things over there. So there you go.